Hi, I'm Nicolò Zenoni. First, I would like to thank the organizers for the opportunity to present this work in progress. In this video, I'm going to talk about a falling magnetic monopole as a model for a holographic local quench in the ADSCFT context. ADSCFT is a correspondence between a theory of gravity in anti-de Sitter spacetime and a conformal field theory on anti-de Sitter boundary. This correspondence allows us to describe strongly coupled conformal field theories in terms of weakly coupled gravitational systems that are, in general, much easier to be studied. ADSCFT, among several applications, gives us the opportunity to explore quantum systems at strong coupling and far from the equilibrium. An example of non-equilibrium process is the local quench, representing the evolution of a system after the localized injection of energy. In the ADSCFT framework, this process corresponds to the free falling of a massive particle in Poincaré anti-de Sitter spacetime. Let us consider as initial configuration the particle at its turning point. In the dual CFT on the boundary, this corresponds to excite a finite region with the same size as the distance of the particle from the boundary. Then, as time passes, the particle falls deeper into the bulk, while in the dual CFT, the perturbation propagates at speed of light and is damped. An interesting question about this model is whether and how the details of the falling particle affect the physics of the dual CFT. To gain some insight, we consider a falling monopole and we compare the result with a falling black hole. Before describing a falling magnetic monopole, it is convenient to start from a static one. We specialize to 4 spacetime dimensions, and we consider a model with a massive scalar and an SU2 gauge field. In the case in which these fields do not backreact on the geometry, a solution to the Einstein field equation is global ADS4. In this setup, a monopole solution is known, and it is given by a generalization of Tooth-Polyakov ansatz, in which the scalar field looks like a hedgehog. Both the scalar and the gauge field contain profile functions h and f respectively, whose boundary expansion is crucial for the physics of the dual CFT. In particular, the leading order coefficient in the gauge field expansion is interpreted as a background source, explicitly breaking the SU2 symmetry in the dual CFT. To avoid this, we therefore put to 0 this coefficient. However, this background geometry is just an approximation, because in general, field will backreact on the metric, changing it. In this case, we take as an ansatz for the metric with backreaction a deformation of global ADS4 metric by the introduction of these 2 functions h and g. We require that both h and g tend to 1 at the boundary in order to asymptotically recover global ADS4. This ansatz describes both a black hole in global ADS4, with which we want to compare our results, and a magnetic monopole in global ADS4. However, in this case, we don't have exact solution for h and g. But for our purposes, it is enough to work in the small backreaction limit, taking a first-order expansion of h and g in this parameter epsilon. Here, I show the monopole numerical solution for the unperturbed profile function of the scalar field and the gauge field, and also the metric functions at first order h and g. I will use these numerical values for the following plots in this video. So far, we have considered a static particle in global ADS. Now, we perform this coordinate change, mapping global ADS to Poincaré ADS and making our geometry time-dependent. As a result, the static particles will now fall into the bulk of Poincaré ADS spacetime following this light blue trajectory. This change of coordinate also affects the boundary expansions of the profile functions for the scalar field and the gauge field. With our previous choice, the coefficients of the leading term expansion in the gauge field still vanish. As a consequence, there is still no explicit symmetry breaking in the dual CFT, even after this coordinate change. On the other hand, the two coefficients alpha tilde and beta tilde call for a physical interpretation. The most natural choice, as we will see in a moment, is the so-called triple trace deformation. This consists in adding in the conformal field theory action a term containing the fourth power of a scalar operator whose vacuum expectation value is alpha tilde. So, we have now completed the description of our gravitational system. We can now move to the collection of results regarding the dual CFT. One way to study the dynamics of the CFT is to compute the energy momentum tensor. This can be done holographically by the following recipe. Going to the triple trace boundary conditions, we find that the energy momentum tensor is traceless and conserved. And that's the reason why this triple trace quantization is the most convenient one. The time-time component of the energy momentum tensor, interpreted as the energy density in the dual CFT, has the qualitative behavior we expect from a local quench. In particular, we have a peak at initial time in the excited region, and then a 45 degrees tails at later times, telling us that the perturbation is propagating at speed of light. It is important to note that the energy momentum tensor does not distinguish between a monopole and a black hole, despite of this multiplicative constant, which at least in the parameter region we studied is positive. Another quantity characterizing non-equilibrium processes is the entanglement entropy. This can also be computed holographically by the Ryuta-Kyanagi formula, relating the entropy of a boundary state restricted to a subregion D to the area of a codimension 2-extremal surface into the bulk. We don't have exact solution for our metric. However, we can compute the entanglement entropy variation with respect to the vacuum. For simplicity, we work at first order in the back reaction parameter, and we consider as a subregion a disk of radius L. Here, I show the results for a black hole and for a magnetic monopole for various values of the disk radius L. The corresponding curves in the two models have the same qualitative behavior, with the important difference that the area variation is positive for a black hole and negative for a magnetic monopole. This has important consequences regarding the validity of the first law of entanglement entropy. To understand this, let us consider a vacuum state in our quantum field theory and a family of states ρ parameterized by this small epsilon. At first order in this perturbation parameter, the difference of entanglement entropy of ρ and sigma equals the difference of the expectation values of the modular Hamiltonian for the vacuum. This is called first law of entanglement entropy, and it has been shown to be valid for time-independent backgrounds in some cases. Using our holographic results, we can test the validity of this first law, and it turns out that it is true for a black hole for small size subregions, while it is not true for a magnetic monopole. This violation of the first law agrees with what has been found in the literature for backgrounds with scalars assuming non-trivial expectation values. So, summarizing, we have seen that a conformal field theory local quench has the same dynamics as a free-falling particle in anti-de Sitter spacetime. Considering a black hole and a magnetic monopole, we have seen that the energy momentum tensors have the same functional form, whereas the entanglement entropy is sensitive to the details of the falling particle. Interesting future development could be to compute the entanglement entropy for different subregions and test if this distinction is solid. Moreover, it would also be interesting to interpret our holographic results from the conformal field theory point of view. Thanks for your attention.